we go. Yes. Good. So, guys, that's the crazy bit. So, chapter 4 book? No, not 20. No. Yeah, no. What's aqueous chemistry? It's not chapter 5 because that's electrochem. 4. I was right. Guys, chapter 4, aqueous chemistry. And when we did aqueous chemistry, we talked about net ionic equations and precipitation reactions. And this was in August, you guys. And we talked about net ionic equations and precipitation reactions. And then we talked about acid-base reactions. And when we talked about that, I said, guys, we're going to learn just enough so that we can sort of play with this. And then we're going to spend 5 weeks and really get into this. And you just took that test. And then, guys, the next to last concept in chapter 4 was redox. And we defined it briefly, and we said we might just need to know a little bit about this, but we're going to spend a whole unit on this when we talk about electrochemistry. But guys, do you remember what I said? Guys, when this happens in March, it will be the last unit of the year. And when that unit's over and it's really small, we're going to spend the rest of the year getting ready for the AP test. We're there now. The test is tomorrow. Oh, yeah. So, guys, with that said, how is this going to unravel? So, guys, today what you're going to do, what we're going to do, is we're going to define some terms. But, guys, understand these definitions are perhaps as worthless to you. Jacob just got his mission call, so apparently, is that true? Okay, so this maybe fits together. Because where do you go before you go out into the mission field? The temple, but eventually to the MTC, right? And in the MTC, the LDS Church, and you guys know this, has created one of the most wildly effective language acquisition programs in the world. They get knot-headed 18-year-old guys and 19-year-old girls to learn a language faster than any other language acquisition program in the world. You guys understand that? Of course, they have the motivation that you're a scared 18-year-old that knows you could starve to death if you can't ask, where do I get food, right? You're about to be in Thailand and it's going to get real. That's a lot different than Spanish class downstairs when Guyver's trying to teach you Spanish and you're like, I'm going to walk out of here and speak English for the rest of my life. It's a different motivator, right? But guys, the trick here is that when you get involved in that language program at the MTC, they're not just telling you the definitions of words. It's not about vocabulary acquisition. It's about changing the way that you think. And if you've had siblings or friends that have been out in the mission field, you've probably had this conversation with them where they will, email home now. It used to be write home, but they'll email home and they'll say, something really weird happened to me last night. You dreamed in your native language, right? And that's when you know that it's there. Because up until that point, it's the continual process of translation. You're thinking to yourself, where do I find food? And then your brain goes, donde come fu? I need food, right? And you think it in English, and then you hurriedly translate it to Spanish, and then something comes out of your mouth. And you know that you're there when your brain subconsciously is now thinking in that other language. Now, guys, the same thing needs to happen to you, and this is not really a stretch. The same thing needs to happen to you in here, because we're going to be talking about oxidation and reduction. And you're going to find out in a minute that oxidation is the losing of electrons and reduction is the gaining of electrons. And at first you're going to be translating. You're going to be asked, is this thing being oxidized or reduced? And you're going to go, okay, oxidation, oil rig, lube gain, and then something may come out of your mouth. Because what you're going to find is that in the same way that a missionary is fluent in that language, I'm fluent in this because I've been doing this long enough and I don't have to go through that process. I can visualize what reduction looks like and consequently I can talk about it without translating. You need to get to that point too. Now at first you're not going to, and I'm going to give you all the stupid little acronyms and all the little tricks. But guys, eventually you're going to have to get to the point where you can go, that's being oxidized. And understand the only way to get there is by practicing the language. So how do you practice? And guys, honestly, the way to do it is by writing. And that's what you're going to be doing during your homework. So I would encourage you to be thorough as you're doing your homework because it's as much language acquisition as it is concept representation. You know what I'm saying? Does that make sense? Okay. So, guys, let's give you the tips and tricks. Ready? So, background for oxidation reduction. It goes like this, because this is all it is. Oxidation reduction reactions are simply reactions that involve the transfer of electrons. Guys, I'm realizing that I'm flying without a net, and I think I can easily get away with it after the first 2 slides. But I'm thinking I'm going to be better served if I just print these. So let me do that. Go ahead. Yes, actually they will because what they see is what happens up there. Mr. Smarty Pants. Okay. So guys, here's the problem. So we understand that, well, we know, we don't understand, but at least now we've been exposed to this idea that oxidation and reduction involves the transfer of electrons. Now the problem is we can't see electrons, right? So in the same way that we've never seen a black hole. You guys know that, right? We've never seen a black hole. By definition, you can't because they're black. They're so massive that light, the gravity of this dense mass is so great that light can't get out. You can't see a black hole. So what evidence do we have that black holes exist? Well, the absence of light, but it could just be dark sky. Oh, things orbiting it, things getting sucked into them. And light. So guys, what we do, and all of it's cool you guys know some of these, but guys, the thought being this, the evidence of something many times is not the something, it's the changes that occur because of that something. And guys, we do the same thing here. We don't see electrons. So how do we know electrons are moving? Well, guys, electrons have a charge, right? And as the electrons move, the things that are involved experience charge changes. So, guys, the evidence that we use is a change in oxidation number. Remember, oxidation numbers are the charges that atoms take on as they gain or lose electrons. So our evidence for oxidation reduction processes are changes in charge. So now, guys, we've got to be careful. And every year I hesitate to make this connection because it's not a great one. But I fear that given what we just got done covering, some of you are going to make this connection anyway, so we may as well just talk about it. So think about this. Can you have an acid without something being a base? What do acids do? They give away hydrogens, right? But they have to have somewhere to go. Because, guys, even when we do this, even when we say HCl yields H and Cl, what are we assuming is really going on? The hydrogen's going to water and forming hydronium. Guys, I don't know if we've said it, but we need to say it. You can't have an acid without a base. The protons have got to go somewhere. And in the same way, you can't be a base without an acid, because the base takes in hydrogens, which means it needs a source of hydrogen, which is the acid. Well, guys, in a similar fashion, these have always got to work in pairs. You can't have oxidation without reduction. So how does this go? Well, as we transfer electrons, the electrons are being transferred from the atom that is oxidized to the atom that is reduced. So guys, let's just put a fine point on this, and then let's talk about all the tips and tricks. What that means is this. Oxidation refers to the loss of electrons, and reduction refers to the gaining of electrons. And it's funny that I can just say that out loud without even thinking about it. Right. Let's talk about why it isn't.
Wait, sorry, I was right.
Yeah. It's okay. Just a second. I want to talk about all of this, but as Daniel said, hold on, I missed that because I was writing. The irony of that taking notes is interfering with your learning, but we talk about this all the time and you guys can't stop. So let's just write it down. I know, I was making me nervous because Isabel's actually making eye contact right now, and I'm like, this is freaking me out. I'm like, wait, she's normally, why isn't she taking notes? I was proud and yet disturbed. Are you okay? Are we good? Okay, so what did you want to say? Electron is reduction gain. What? Right. Exact, and that's where the name comes from. So, guys, it's cool. Gwen picked up on this. So they actually named oxidation first, and we'll talk in a second. But when they were talking about the opposite process, the gaining of electrons, they called it reduction because electrons are negative, right? And if I'm an element that is taking in electrons, because those electrons are negative, what happens to the charge as I take in electrons? Goes down, and that's where reduction comes from. Now, if that's true, and it is, and it's neat you picked up on that, where does oxidation come from? It's oxygen, right? Now, guys, let's talk about our good friend oxygen. So we know some things about oxygen. First thing that we know is that oxygen has got two bonding sites. It's got two places that it can take in electrons. But what do we know about the electronegativity of oxygen? It's pretty high, right? Certainly not the top of the charts. Fluorine is stronger. But oxygen, let's talk about it. Oxygen is small. Oxygen is highly electronegative. Oxygen's got space for 2 electrons. So, guys, and this was like mid-1800s, maybe a little earlier, when they started studying these processes where electrons were being gained and lost, what they found was that elements, especially metals, liked to lose electrons. And why do metals like to lose electrons? Big and fat and weak, right? And so when they lose electrons, as they're losing these electrons, where did those electrons just tend to go out in our world? To oxygen. But now you're thinking, but wait, well, why not fluorine? Because fluorine can take in electrons and it's even more electronegative. So why do we call this oxidation and not fluorination? Because oxygen's more plentiful. So as they were first studying this, they were seeing that metals love to give up electrons to oxygen. We have a different name for that though. What do we call that process? Rusting. Guys, that's what happens when a metal rusts. It's simply losing electrons to oxygen, and then the negative ion and the positive ion bond together, and we get oxides, which are rust. Iron oxide is rust. But that's what's happening. The iron atoms are losing electrons to the oxygen atoms, and as that process happens, oxygen becomes negative, the iron becomes positive, ionic bonding, and that oxide salt, which is rust. But because oxygen loves to make this happen in other elements, they said oxygen is doing this to these metals, so let's call it oxidation, because that's what's happening to these other substances. But now, guys, we got to be clear on terms. Oxidation is not what's happening to the oxygen. Oxidation is what the oxygen's doing to the metal. So oxidation is the loss of electrons, and they called it oxidation because that's what oxygen does to metals. Does that make sense? Is that okay? Okay, so that's the history. So then the question becomes, how are we going to remember that? Well, guys, I like this. My rule of thumb is the charge of the atom that is reduced is reduced. This was Gwen's observation. And it really is where it comes from. As I said, I don't have to think about it this way anymore, but you may, because you're just cutting your teeth on this. And if you get into this and you're like, whoa, I need to think and then translate, perhaps you think which one's charge is going down, and that's the one that's being reduced. Now, sadly, Brandon's not here. Did any of the rest of you go to the University of Utah program over the summer? None of you did, right? But Mary, did you, Emily, one of you two applied. You're in and done and finished and you're done trading letters? Nice. So I want to talk with you more. Because once I send in your name, I am completely out of the loop. I want to learn more. Okay, but guys, you're going to see Mary over the summer, and Brandon learned this last year. At the University of Utah, they teach this. Wow. Apparently at the University of Utah, they can't spell. No, that was actually my fault. Guys, they teach it this way. They teach the acronym oil rig. Get it? Oxidation is loss, reduction is gain. Oil rig. If you like it, use it. No, we didn't do Redox and Gen Chem, so it was probably our August, September time. Yeah. So guys, however you choose to look at this, this gets further muddled when we talk about this. And we've already said this. And maybe we should say this. So guys, redox is simply the bringing together of oxidation and reduction. It sounds stupid to call it oxred, so we put the reduction first, right? So we call these together redox reactions, and that contraction is always appropriate because you can't have one without the other. Now, what you're going to find out is in a couple days, we are going to talk about the concept of agency, and I'm just going to give this to you. When we talk about oxidation and reduction, we're talking about what is happening to the substance itself. The thing that's oxidized is losing electrons. The thing that's reduced is gaining them. But because we understand these always have to happen in pairs, we will also later talk about the idea of these things functioning as agents. So an oxidizing agent causes oxidation in the other guy. It itself is reduced. And similarly, a reducing agent causes reduction in the other guy. It itself is oxidized. It loses electrons, and those electrons reduce the other guy. So when we talk about this idea of agents, we are talking about what they're doing to the other thing. Guys, don't get hung up on this now. I just find it useful to share it with you so that when we talk about it in 2 class periods, you're not going to go, huh? Because we're going to spend a whole day on it. All right. Right, kind of. Don't talk to me about that. Don't ever. My son's going through that right now. Can I? No. No, I know. My son came to me, Dad, I don't understand the unit circle and I don't get all this stuff about inverse trig functions. And I almost vomited. Is that a thing? I don't even know. I don't know what I mean. I just know that I've repressed all those memories. I got to be careful. I have friends on the other side of the hallway. I can't be bad-mouthing this stuff because they find it wildly important. All right, you guys all caught up? Okay. You guys good? All right, so guys, let's do this then. Why do we care about this stuff? Well, this stuff is everywhere. I mean, we understand rusting is an oxidation-reduction process. We're going to talk about it in a different context, but let me give you the big picture. So guys, what you're going to find out is that many redox reactions are spontaneous. Seldom are they at equilibrium. They have a direction. And many of them tend to be, well, usefully spontaneous. They also tend to be exothermic, which explains some of their spontaneity. But guys, the thing that's neat about these is that because redox is a exchanging of electrons, and because a flow of electrons we call electrical current, because this becomes interesting in the context of batteries. Because every single battery on this planet anywhere is just an oxidation-reduction reaction. Every single battery. It doesn't matter if it's the battery that's in Elon Musk's Tesla or your cell phone, and actually they're very similar batteries, or the battery in my truck that died over the weekend, because it doesn't matter. They're all just oxidation-reduction reactions. And when we talk about batteries, it's fascinating chemistry, and we're going to talk about how batteries work. We're going to talk about what happens when batteries die. And we're also going to talk about the fact, guys, that if you really want to change the world and make a lot of money in the process, spend your life developing batteries. You guys understand, we don't have an energy production crisis. We have an energy storage crisis. Do you guys understand that? That we could very, very easily create enough clean, renewable electricity to power this world forever. The problem is we've got nowhere to put it, because the wind doesn't always blow and the sun doesn't always shine. And we don't always have water to fall off a dam. And guys, consequently, we need a way to store electricity, and that's batteries. And we're not very good at batteries. But if we get good at batteries, it's going to be a different world. And you're going to make a lot of money. And because of this talk that we just had, you're going to come back and give me some of that money. You think I'm kidding? It would be a nice touch. Wouldn't that be great if a student came back and said, "You set my life on this path, and I just wanted to write you a check"? Heck no. It's a risk I'm willing to take. I don't know. Yeah, I mean, why not? You can give money to whomever you want. So, guys, here's the interesting thing. When these processes are not spontaneous, we can make them happen by applying a current. That's how we make gold-plated jewelry. You take a piece of copper and put it in a gold solution and not much happens. You pass a current through it, the gold plates to the copper. You have this is interesting, you have a battery and it dies. What do you do if it's rechargeable? Well, you recharge it. And guys, every time you plug your cell phone into a charger, that's what you're doing. You've got a reaction inside a battery that's spontaneous. And as that reaction takes place, it creates current and loses energy. So what do you do at night? You plug it back in. And what does your battery charger do? It simply reverses that spontaneous process and drives it in the non-spontaneous direction, recharging the battery so it's ready to go in the morning. Guys, that's all a battery charger is a source of energy that drives a spontaneous direction in its non-spontaneous direction, resetting or recharging the battery. That's all a battery charger does. We're going to talk about that too. And then, guys, finally, we are going to talk about all of these things. Batteries, electroplating, corrosion of metals. Yeah, with plenty of time. That's what we're going to do. You guys good? Y'all caught up? Okay. So guys, in order to do this, the first thing that we need to do is let's consider this reaction. And I think you could balance this pretty easily, so I'm just going to give it to you. So zinc plus hydrochloric acid. All of my general chemistry students just did this first period. Remember that when you collected the hydrogen in the test tube and stuck the wood splint in there and it went boop? They just had that experience. So guys, this is the chemistry. Don't write it down. This is the chemistry of that reaction. The zinc is reacting with the hydrochloric acid, and as it does, it produces zinc. Actually, you know what? I take that back. Let's write this down. And do this. Guys, skip down 2 lines and write it as wide as your page. I was going to have you. Is that a good sentence? Kind of. Yes. We're going to pick this apart together. Thanks. I don't know what I'm saying. What was the name of that conference you guys are going to remember?
Weekend to Remember.
Could be. It's. That's right. That's right. All right, guys, so here we go. This reaction is what kind of reaction, given what you know previously? Single, double, synthesis, decomposition, combustion. Single displacement. An element with a compound, the chloride is, or the hydrogen is being displaced, the zinc hooks up with the chlorine. Single displacement reaction. Guys, the thing that you don't know is it's also a redox reaction. So how do we know? How do we know that electrons are being exchanged? We're looking for charges. So guys, do this with me. So let's start with the hydrogen, the hydrochloric acid. So guys, what is the charge of hydrogen? You probably know that it's +1. What is the charge of chlorine? It's got to be -1, right? Because those balance. Now guys, let's go over and look at zinc. Here's the rule. The charge of an element in its elemental state, zinc, is 0. You may remember that from having looked at the chapter. Now guys, let's move over to the right. Chlorine is still -1. It's the only negative charge that it can take on. What's that? It doesn't, and here's why. What's the charge of zinc? Can you see it there? You probably can't. But guys, what does it have to be if there's 2 -1s? Yeah, +2. Now guys, interestingly this. What is the charge of H2? The whole thing is 0. That is the elemental form of hydrogen. That is understood to be 0. So now guys, here's what I want you to do. First of all, identify the spectator in this reaction. Who's our spectator? Chloride, right? So guys, chloride starts as an ion dissolved in water. Chloride ends up as an ion dissolved in water. Chloride is our spectator. Now guys, let's do this. Draw a line, much like mine, between the zincs. Then guys, draw a line and watch before you do. Maybe a little lower between the hydrogens. So now I want you to ask and answer 3 questions relative to each of these species, zinc and hydrogen. So looking at zinc first, here are the questions I want you to answer in your head for now. Thinking of zinc, did it gain or lose electrons? Is that oxidation or reduction? And how many did it gain or lose? What did it do with electrons? What does that mean it is, oxidation or reduction? And how many electrons did it move? So hold on, let people think. So guys, let's start on the first question. Did zinc gain or lose electrons? Lost electrons. Its charge went from 0 to +2. So zinc lost electrons. Perhaps we could answer the third question second. How many electrons did it lose? 2. Now, when it lost electrons, is that the process of oxidation or reduction? Oxidation, good. So let's write that down. Oxidation and 2 electrons. That's our electron loser. Now, we know by process of elimination that hydrogen's got to be the opposite, but let's go through the exercise. So guys, hydrogen went from +1 to 0. What happened to its charge? It went down. What is that? Gained electrons. That's reduction. See how all those interesting thoughts fit together? But now, let's talk about electron count. So guys, hydrogen went from +1 to 0. So how many electrons did it gain? 1. But how many of them are there? 2. Do you see that? There are 2 hydrogens, each one of them gaining 1 electron for a total electron exchange of 2. Now guys, understand that is not coincidence. In the same way that there is a law of conservation of mass, there is a law of conservation of electrons. You cannot gain more electrons that you lose, or vice versa. So when you get into these and you find that your electron gain and loss counts don't match, what does that tell you? The electrons, the equation's not balanced properly. Does that make sense? Okay. So now, guys, and I want you to do this in your writing, and I'm going to earn you some more points on the AP test. Ready? I want you to do this. I don't care who you think you are. I want you to do this. I want you to write 2 quick sentences. You're going to see these questions on the AP test. Question number 1 is this. Which substance is oxidized? I want you to write down blank, fill in the blank, is oxidized. And I want you to write it out in words. No abbreviations. I want you to write it out in words. What substance is oxidized? Don't write the abbreviation. And then the second is this. What substance is reduced? Fill in the blank as words. Second only to intermolecular force questions on the AP test, because you know those are statistically the hardest questions on the test. This is second. If there's an electrochem question on the AP test, and if there isn't in free response, there probably will be some of these in multiple choice. Guys, this question kills people. Let's talk about why. So guys, what substance is being oxidized? Zinc. Yes? Zinc is being oxidized. What substance is being reduced? It's not, that's it. It's not hydrogen. It's not hydrogen. It is hydrogen ion. So now you're going, well, that's stupid. It's just a word. Guys, what does this look like? This is but what does hydrogen look like? What do you experience when can you picture balloons? No, because we don't do that anymore. We do helium. Can you picture the Hindenburg bursting into flames and Germans falling to their death? Guys, this is you guys haven't seen those videos? You guys are aware of that, right? Where the Nazis were using, they call them dirigibles, blimps, they rained terror down on London. You didn't hear them coming. And guys, the Nazis were using blimps to horrible effect in World War II. But then they started using them as also passenger vehicles. And they were filling these balloons, interestingly, with hydrogen. And it was to make an airtight bladder, they were literally using the stomachs of cows and stitching them together They were killing hundreds of thousands of cows just to get their internal organs to make these things airtight. It's crazy, weird stuff. But guys, they were filling these balloons with hydrogen because they couldn't isolate helium well enough because it's a noble gas and it's hard to get a hold of. So they were filling these balloons with hydrogen, and they were bringing one of these blimps in to dock on this mooring tower, and it was in a storm, and the blimp became static charge, just like you do when you drag your feet on the floor. And as this thing closed in on that tower is connected to the ground, and a spark jumped, and it lit that thing on fire. And it's horrible. They were celebrating as Germans, look at our power and our pride in this. And all of these news reporters and civilians that were in the carriage of that blimp, and they're 100 feet off the ground, and this whole thing is just going up in flames, and people are jumping to their death. I mean, it's horrible. But guys, understand that's hydrogen gas. Guys, what's this? Those are hydrogen ions swimming around in water doing acid stuff, right? That's not hydrogen gas. So again, the answer to what is being reduced is not hydrogen. It's hydrogen ion, and those are not the same. That is not a word game. That's chemistry. You guys good? Hold on, let's go ladies first. What? So hydrogen is this clear, colorless, odorless, very reactive gas. Hydrogen ion are protons in water functioning as an acid. The difference is an electron. Hydrogen with electrons is a gas. Hydrogen missing one electron is a proton dissolved in water, because that's the only place it's stable, doing its acid things. Go ahead, man. You sure? Okay. So guys, what are we then going to do with this information? Well, the answer is this. What we need to do is we need to gather around where we're at so we can figure out where we're going. So guys, as we get into this, what you're going to learn to do today is you are going to learn to balance redox reactions. What I'm going to do is give you the steps to do this. But before we do, there's one more thing we need to talk about. So guys, we've got to understand that and this is how we're going to wrap up the day, we're going to learn to balance oxidation-reduction reactions. When we balance these, and we already sort of alluded to this a second ago, when we balance oxidation-reduction reactions, it's no longer just law of conservation of mass. It's also electrons in have got to equal electrons out. Now, in order to get all of that to happen, this process becomes a little complicated. So you ready? How long has it been since you've seen that word? Steps. Steps. Since general chemistry. Guys, remember how in general chemistry everything had steps? How do you solve mass problems? Step 1, write a balanced equation. Step 2, start with the mass of a reactant. Step 3, set your goal at the mass of a grams of product. And guys, everything in there was steps. Because the majority of your classmates were so helpless that if we didn't give them steps, they'd die on their own. That's what makes AP chemistry hard, right? All the steps go away. And you've got to figure out things on your own. Well, guys, I'm going to give you steps. Ready? Here's how to balance redox reaction. Step number 1, write the half reactions. I would write this one down. These are steps. They don't have numbers, but they are steps. Step number 1 is write the half reactions. What does that mean? I'll show you in a minute. Step number 2, you are then going to balance. And you have to do these in order. First of all, you're going to balance other elements. Other than what? Hydrogen and oxygen, and it matters what order you do these in. Next, you're going to balance oxygens by adding water. Then you're going to balance hydrogens by adding protons. Then you're going to balance the charges by adding electrons to the side with the greatest overall positive charge. You will never subtract electrons. You will always add electrons. Then after that, you will multiply each half reaction so that the electrons balance. Then you will add the two half reactions and simplify. Then, if you are in a basic environment, you will add hydroxide to get rid of the protons, converting them into water. Then when you're done with that, you will check your work and make sure that you are in fact balanced in accordance with the laws of conservation of mass. And then finally you will curl up into a ball and cry.
I'm surprised if you put that on the board.
Never be surprised. So, guys, as you're writing all of this down, here's the deal. If there, and it's been a long time, but never say never. If they put a question on the AP test that says balance this oxidation-reduction reaction, I don't care if it's in multiple choice or free response, doesn't matter. If they put this on the test, skip it. Don't do it. Only come back to it if you have checked and double and triple and checked every other part of the test. Don't do it. It takes forever and you're probably going to get it wrong anyway. Skip it. Oxidation-reduction reactions on the AP test are bait for suckers. Don't get sucked in, guys. Don't do this. With that said, guys, I seriously, since I switched AP books about 9 years ago, I've been trying to balance the same two oxidation-reduction reactions in front of my students for 9 years. Finally, last year, I did it without making a mistake. For 8 years, the same reactions every year. It took me 9 years to finally do both of them without making a mistake. We're going to see if we can go 2 in a row. But I'm not in any way hopeful. And it's not me being stupid trying to make mistakes on purpose, because you know I like to do that. This is really me going, oh, poop. So we'll see. Yeah.
So when I was reading the chapter summary, or the chapter, it had the same steps, and it also had a section about why it's different with the basic environment. I didn't see one if it's acidic. Why doesn't it happen?
You'll see. We'll talk about that in the context of this. But fundamentally understand that oxidation-reduction reactions happen always in water. There we've got something like an acid and base. But perhaps in acidic environments or basic environments, those encourage these reactions. And we honor that by balancing hydrogens by adding protons. And so there's your acidic environment. But if you are in a basic environment, you don't have an excess of protons, you have an excess of hydroxides, and we deal with that at the end. It'll make more sense when we get into it. Now guys, in order to get into this, I would suggest we need to talk about step number 1, right? What are half reactions? Guys, don't write this down, please. No, you know what? Yeah, you guys are going to do this anyway. Let me show you. Oh, I wonder, this isn't going to line up. You know what? I'm just going to have to bring this in. So guys, here's our reaction. So what are half reactions? Don't write this down. You don't need the definition. Let me just show you. So half reactions go like this. You can take an oxidation-reduction reaction, and guys, you can think of it as being 2 independent reactions. One of those reactions being the oxidation. Zinc losing electrons, that's oxidation. The other is the reduction. And guys, when we break these into half reactions, we go like this. Zinc is turning into zinc ion. Do you see how that's reflected in what's above? Now guys, when zinc turns into zinc ion, what happens to the zinc to turn into zinc ion? Loses electrons. How many electrons? 2. So we represent it like that. Does that make sense? So the zinc is losing electrons to turn into zinc ion. Now guys, notice importantly, and I'm just going to chicken scratch this, notice that we don't write it like this. We don't think of it as zinc losing electrons. It is losing electrons, but we don't write it as zinc minus electrons. We think of it as zinc turning into zinc ion, and then the other product is these 2 electrons. Does you see the distinction? It's never minus electrons. Now guys, where do those electrons go? Where do those electrons go? They go to the hydrogen ion. So our other reaction then would be 2 hydrogen ions plus those very same 2 electrons, giving us diatomic hydrogen gas. These are the 2 half reactions that represent the overall reaction. One of them is the loss of electrons. Is that oxidation or reduction? Oxidation. So in your oxidation half reaction, let's see if you can put this together. In your oxidation half reaction, where will the electrons always be? Which side?
The
Products. Let that soak in for a second. In the oxidation half reaction, your electrons will always be products. They're being released. And then, guys, in your reduction half reaction, the electrons are going in. They're on the reactant side. Does that make sense? Now, guys, what happens if you're writing out your half reactions and you've got electrons on the reaction side in both of your half reactions? Something's wrong, because you can't have 2 reactions both taking in electrons. You can't have 2 reductions. You've got to have one of each. So the oxidation, the electrons are on the product side. The reduction, the electrons are on the reactant side. You guys good? Okay. Here we go. What do you think? Am I going to do this without screwing up 2 years in a row? I am not helpful. I'm not helpful. I'm not hopeful. Here we go. So guys, you see this on the test and you go, gosh, that looks simple. You've got the reaction that says iodide, write this down with me. Iodide ion plus iodate ion yields the triiodide ion. How hard can that be to balance? I'm going blue. Here's what you're going to do. You ready? You with me are going to draw a line down the middle of your paper, make it about 8 lines tall. If you don't have 8, flip your paper over. Do not try to do these by flipping from the front of the back to your page. Now guys, this is going to be the grace that I'm going to ask from you. If you play chess, I don't even know if this is a rule, but if you play chess the way that I play, which isn't often because chess makes me angry, but if you play chess, I believe that there's a rule that says your move doesn't count until you take off your hand. Is that? I don't know if that's a rule, but I'm going to ask for that rule here. What I write doesn't count until I take my pen off the board. So if I screw up, it doesn't count until my pen comes off the board. I don't know. Let's see how it goes. So guys, here's what we're going to do. To write this balanced equation, to balance this, step number 1, break this into half reactions. Now this is weird because we only have one product. Just watch. It'll make more sense in the second one. Just watch. So here's what we do. We take our first reactant, I negative, and that forms I3 negative. Now our other half reaction is IO3 negative yields I3 negative. So we've broken this into half reactions. Now guys, the bell's gonna ring. 10:10. We're gonna work through the bell, take a break, come back and talk about pH probes. Here we go. Ready? I need the steps in front. Can I get to use the steps.
Wait, but then how are you gonna mix that?
Oh no, you just wait. I'll find a way. Okay, so guys, ready? Step number 1 done. Balanced equations. Or I'm sorry, half reactions. Now we need to start balancing these half reactions, and the first thing that we balance is everything that's not oxygen or hydrogen. So 1 iodide, 3 iodides, so we go 3I minus yields I3 minus. Now over here, we've got 1 iodine, 3 iodines, so we're going to go 3IO3 minus yields I3 minus. We're just following the steps. Follow the steps. You guys okay? Can you tell I'm nervous? I'm a little nervous. Okay, so here we go, guys. Then we're going to balance the oxygens. So watch. This is why I wanted to do this one first, because it brings up some weirdness. So this doesn't have any oxygens, right? This is my suggestion. Write it down again. The reason being, you are going to apply the same balancing process to each half reaction step after step. And if these get out of sync, you're going to forget what you have or haven't done to these as individuals. It's really nice if they fall down the page together. So now let's go down. We're balancing oxygens, right? How many oxygens do we have on the left? 9. I'm sorry, on this guy, the other half reaction, on the left of the other half reaction, we have 9 oxygens. So how do we get 9 oxygens on the other side? I don't ask that rhetorically. Add 9 waters. Oh yeah. Action. So there's water available. No, we'll talk in a minute. Okay, so now guys, we've balanced the oxygens by adding water. Now we're going to balance the hydrogens by adding protons. So again, in this left-hand reaction, there are no hydrogens. So I'm going to rewrite it. Okay, now we need to talk hydrogens. How many hydrogens are there in our right-hand half reaction on the product side? 18. So we need to go 18 protons plus 3 IO3 minuses yields I3 minus plus 9 waters. Okay. So now, guys, the next step. We've balanced elements, we've balanced oxygens, we've balanced hydrogens. Now we need to balance charge. I'm going to switch colors so this stands out. Guys, left-hand half reaction, what is the total negative charge on the left if we've got 3 negatively charged iodides? -3. Now, what is the negative charge on the right-hand side if we've got 1 I3 ion with a -1 charge? We're going to keep going. -1. Now, here's the idea, guys. Watch my hands. If this is 0, the charge over here is -3. The charge over here is -1. Now we need to make these equal. Again, -3, -1. But the only way we can make them equal is by adding electrons. So what are we going to do to make these equal? Add 2 electrons to which side? The right, driving it down to -3. Does that make sense? So we're going to do this. Switching back to blue, we're going to go 3 I minuses yields I3 minus, and then we need to add 2 electrons to drive the charge on the right down to -3. You good? Now we need to play the same game on the right-hand half reaction. So we have a positive charge of 18, just looking at the reactant side, a positive charge of 18 and a negative charge of what? -3. So bringing those together, I believe we have a positive charge of +15. Okay. Now on the right, it looks like we just have a negative charge of -1. Am I thinking about that right? Okay, so now guys, watch my hands again. If this is 0, we've got +15 and -1. How do we bring those together? 16 electrons. To which side? The left. So we now have this. 16 electrons plus 18 protons plus 3 IO3 minuses yields I3 minus plus 9 waters. It just has to be on the reactant side. Now guys, let's pause. Left-hand half reaction, right-hand half reaction. Which one's oxidation and which one's reduction? Let's look. What's the one on the left? Is that oxidation or reduction? How do you know it's oxidation? It's losing electrons. So what's going on over here on the right? Reduction, because it's taking in electrons. Now guys, what if you had plus electrons on the reactant side of both of these? You did something wrong. What if you've got electrons as the products in both of these? You also did something wrong. So guys, this is an important place to pause and go, am I okay? If you have electrons, one is a reactant and one is a product, you might be okay. If that's not the case, you're not okay. If that's the case, what do you do? Start over. But we're okay. So now guys, the next step. It is now time, following the steps, multiply each half reaction by a multiplier. Let's screw this up. Yeah. First time in 9 years. It was a moment. So guys, we need to multiply the half reactions by some multiplier that makes the electrons equal. Just the electrons. So we've got 2, we've got 16, so I need to multiply that by 8. So let's do it. So guys, 3 times 8. Sorry, I'm just making sure I'm still in blue mode. So 3 times 8, 24 I minuses yields 8 I3 minuses plus 16 electrons. Now guys, at this point, you don't need to rewrite the one on the other side, because you're now done with the parallel manipulations. You're now ready to bring them together. So here's what I like to do. I like to draw a line. Mr. Ellingford the funny thing is somehow we were talking about donuts earlier, Is this why? That was like a prophetic thing you were doing. You knew this was coming.
She anticipated it.
For what?
For excellent work on peer revision. She's one of 3 AP kids that actually revised over the weekend.
So let me understand. You are rewarding the kids simply for doing what they should be doing.
That's what the times have come to.
It's the Orem High School way. Give that girl a donut.
Isn't that nice? Isn't that nice?
High school way. You got spared grades, you get ice.
Oh, thank you, sir.
What do you need, guys?
Okay, guys, you ready? Here we go. We're now going to, this is going to kind of feel like Hess's law, or perhaps the verification process that we do to verify mechanisms, where we add the mechanisms together. We're going to bring the reactants down, we're going to bring the products down. Oh yeah. I didn't say this was going to be fun. So guys, what I like to do is I like to draw a yield arrow in the middle. And then we go like this. We've got 24 iodides over here as a reactant. Then over here, we have 16 electrons, 18. That does not count as a mistake. That was a technical difficulty.
It was a mistake, but not your fault.
18 protons. Oh, now I lost my train of thought. And 3 IO3, bless you, minuses. If I just made a mistake, it doesn't count. All right. Then on the product side, 8 I3 minuses. Don't be trying to mess me up. 8. What?
There's one on the right side there.
Yes, but then like from the
You guys are trying to screw me up. It says 8.
But on the right.
It doesn't matter. 16 electrons. You realize what you're saying is, I'm so good at this, I can just do extra steps in my head. I3 minus and 9 waters. Mr. Nebberg, you screwed this up 8 years in a row, but I'm so good I can do this in my head. Okay. Now, guys, we simplify. If this doesn't happen first, you made a mistake. Did that make sense? If you can't get rid of the electrons first, you did not do this last step properly. Now, guys, what else can we combine together? So, yes, the iodides, and we have 9 of them over here, and we have 24 of them over here. So we can subtract 9 of them from both sides. Is that right?
Wait, but what?
Oh, no, these are I3. I didn't write. That wasn't a mistake. Doesn't matter. Because we live in a litigious society, if you don't get it in writing, it never happened. But what I said was wrong. Guys, these are iodides. These are triiodides. Those don't come together. The hydrogens don't, and we don't have IO3s that come together. So that's all of the canceling we can do. Now we need to do the bringing together. So guys, we've got 24 iodines plus 18 protons plus 3 IO3 minuses. Over here then we've got 9 I3 minuses and 9 water molecules. Now guys, there's one other thing we've got to look for. Do you see it? These are all divisible by 3. So we are going to then reduce this, and I'm not going to write it again. I'm just going to, this is 8, 6, 1, you get it, 3, and 3. Now, guys, we've got one. You know what? I am going to rewrite it because that just doesn't. And I know I'm way probably off the screen relative to what you can read. But guys, let's check. How many iodine atoms do we have on the left? 9? 9? We're just doing, we're balancing equations. So we've got 9 iodines here. We've got 9 iodines there. We've got 6 hydrogens there. We've got 6 hydrogens there. We've got 3 oxygens there. We've got 3 oxygens there, and it balances. Not only did I not screw up, but I overcame Austin's efforts to undermine. Yeah. The speaker of lies. You guys okay? Okay, so guys, let's do one more, especially given that you want to talk about what about this basic environment stuff. No, it was many of you, and it's good. Let's talk. So guys, now let's do another of these, but now it's in a basic environment. This one goes a little faster. So let me do this. Yeah. So guys, divide your paper in half once you've written down the equation. Why don't you set up your own half reactions? Please don't go on past that. I'd like to step through it with you. Do you see now how, guys, we have 2 products? And probably this feels more like what you might have expected it to be. So we've got copper ion on the left. We've got copper metal on the right. Keep the elements together. Then we've got nitrogen on the left, tied up in dinitrogen tetrahydride. And then that creates diatomic nitrogen. So guys, go ahead.
So we just, what if like, how will we always be able to know if another like splitting?
Well, so either you're going to have matching elements on both sides, because stuff can't just go away, or you're going to have one product that both of the substances turn into.
And then in that case, we could just have the same product on both sides, like last time.
Just like last one. Yep. Okay, so ready? Step number 1. Balance every element except for hydrogen and oxygen. Done, right? So you don't write it again. If both don't require adjustment, leave it alone. So now step 2, do we balance oxygens or hydrogens next? Oxygen. And guys, let's think about why. What would happen if we balanced hydrogens next? Then when we balanced oxygens, by adding water, we'd screw up the hydrogens we already balanced because water also contains hydrogen. So balance the oxygens next. Done. Now let's balance the hydrogens. Now we've got to do some work. And because we've got to do some work, we're going to do that work to both sides, even though we don't need to. It keeps them in step. So hydrogens. I've got 4 of them here, which means I need 4 of them on the other side. And in my little brain, that looks like 2 waters. Why does that not seem right? No, that's why. See, I screwed it up. Yeah. I did. Well, no, I'm just consistent. No, and it's not even a 2. Wow. There we go. Okay, so we've done atoms, we've done oxygens, we've done hydrogens, now charge. Okay, so guys, +2 and 0, 0, right? 0, 0. +2 and 0. So which side are we going to add electrons to? The left, because we need to bring that +2 down to 0. So 2 electrons plus Cu2 plus yields Cu. Yeah. Because we're in either an acidic or basic environment, and in those environments, you don't have a reserve. You don't have a source of hydrogen gas. That stuff just goes away. You have a reserve of hydrogen ion in the form of the acid or the base. And I know that seems weird, but we'll talk. So guys, now let's balance charges here. On the left, we're 0. On the right, we appear to be +4, although I've completely broken my confidence. Am I okay? So I'm going to add 4 electrons to the right. Okay. So we're going to go N2H4 yields N2 plus 4H plus 4 electrons. Good. Now what do we need to balance? Yep, so we draw, no, we don't draw a line yet. So we need to balance electrons. We've multiplied the one on the left by 2. So 4 electrons plus 2 copper 2 plus ions yields 2 coppers. And then we can draw our line and our arrow. So then, guys, we bring everything down.
Oh, and if the electrons on one side were odd, we would just double it. We would just...
Yeah, you'd have to double the negative, the one that's odd, and then probably adjust the even one. Yep. Okay, so guys, what if we just didn't write down the electrons? They're going to drop out anyway, right? I have to? Ask yourself, what would Austin do? No, he wouldn't. You realize, Austin, that what is actually happening is you're just taking Brandon's place as the whipping boy. And when he's back, you'll be fine. That's right. So guys, and perhaps we could just say those electrons are gone from there. So then we end up with 2 Cus and N2H4, 2 Cu ions and 2 Cus, N2 4H plus. Okay? So then, does anything combine? It does not. So then, guys, let's do this. Let's make sure that our atoms balance. So we have 2 coppers on the left, 2 coppers on the right, 2 nitrogens on the left, 2 nitrogens on the right. Well, that's a sketchy nitrogen. 4 hydrogens, 4 hydrogens. We okay? Okay, but now, guys, we're not done. And the reason that we're not done is because of this. We're in a basic environment. And in a basic environment, you do not have an abundance of hydrogen ion. What do you have an abundance of? OHs. So here's the trick. Rather than reconceptualize the chemistry, we account for this at the very end. And we're thinking, okay, in a basic environment, we don't have a lot of extra OH. We got a lot of extra we don't have a bunch of extra hydrogen. We have a bunch of extra OH. So the thought then goes like this. we are going to respect the fact that we have lots of OH. And we are going to now bring the OH into the picture. And we're going to say every one of these H's will bond with one of those excess OH's. And what will it then form? It'll form water. But this is how we account for that. We add 4 OH's to here, and we add 4 OH's to here, and then these 4 OH's with the H's turn into 4 waters. Notice here, guys, it still balances. We've got 4 hydrogens here, plus these 4 hydrogens give us 8 hydrogens. And then we've got 4 oxygens and 4 oxygens. But now what we've done is we've converted our hydrogens into water, because that's what would happen. And then to account for the balancing of that, we now have an excess of 4 hydroxides on the left. Yeah? You guys good? All right. So what do I get to tell my classes next year? I can't tell them I did it error-free. I did the first one error-free, pushing through adversity. Right. And then Austin came into my life. Okay, so as